Imagine a biological clock ticking at just a furious, relentless pace. But the organism itself isn't growing a single fraction of an inch.
Not even a millimeter, right?
Right. Over the course of 48 hours, a newly fertilized oocyte systematically slices itself into 2, then 4, then 8 distinct pieces.
And it's entirely trapped inside this microscopic protein shell.
Exactly. It's running completely on borrowed energy from the maternal environment. It's executing some of the most complex genetic reorganization known to science.
Yeah.
It's literally a microscopic locked box of, frenetic activity.
It truly is one of the most profound and really precarious transitions in human biology. I mean, if the zygote stage asked a simple binary question like, did fertilization happen? This new phase asks something vastly more complex.
Which is whether this newly combined genetic code is mechanically capable of executing a flawless geometric division.
Exactly. And we are so glad you are here with us today. In this deep dive, we're zeroing in on the cleavage stage. Specifically, we're focusing on days 2 and 3 of embryonic development. We're going to explore the precise physical mechanics of how these divisions happen, what the embryologists are scrutinizing when they look through that microscope, and what these early structural clues actually tell us.
And critically, what they fail to tell us about the embryo's ultimate potential.
Right.
Okay, let's unpack this. Because cleavage is a term that gets thrown around constantly in reproductive biology.
And he does, yeah.
But we really need to visualize the physical constraints of what is happening in the incubator before we can even begin to talk about how the lab assigns a grade to it. We know the oocyte was previously suspended in the M2 phase prior to fertilization, just waiting for the genetic catalyst.
Right.
So once that catalyst arrives, the cleavage stage begins. But physically, what does that actually look like?
Well, let's start with the most defining physical constraint of this stage. Cleavage stage development refers to the successive cell divisions that trigger right after fertilization. The embryo divides from one single cell into 2, then 4, and progressively more cells, which we call blastomeres. But the absolutely crucial biological reality to understand here is that the embryo does not increase in overall mass or volume during this time.
Right, because it is still tightly encased in the zona pellucida.
Yes.
That outer protein shell is completely rigid right now. It acts almost like a biological corset, holding the entire structure together.
Exactly. Because that outer shell is fixed, the embryo is forced to internally partition its existing volume. It's a closed system.
Got it.
On day 2, which is roughly 48 hours post-fertilization, the benchmark we look for is a 2 to 4 cell embryo. By day 3, roughly 72 hours out, we expect to see a 6 to 8 cell embryo.
It's essentially the geometry of slicing a pizza, right?
That's a great way to put it.
The pizza itself doesn't get any larger, you just cut it into progressively smaller slices.
Exactly.
But taking that analogy a step deeper into the biology, it's not just about physical space. This embryo has a strictly finite energy reserve.
It really does.
It's dividing up the existing mitochondria and the maternal mRNA that it inherited directly from the oocyte. So it has to fuel this massive, demanding construction project without any new raw materials coming in.
What's fascinating here is how that severe energy limitation really dictates the timeline. Those expectations we just mentioned, the 4 cells on day 2, the 8 cells on day 3, they are clinical benchmarks.
But they aren't rigid rules.
Absolutely not rigid biological laws. Cleavage assessment in the lab is a timed snapshot of a highly dynamic, moving target.
You're capturing a single frame of a feature-length film.
Yes, exactly. An embryologist looking at the dish at 8:00 a.m. might record a totally different structural reality than if they checked the exact same embryo at 2:00 p.m.
Because it's constantly changing.
Precisely. The embryo does not pause its development for the microscope. It's in constant fluid motion. The cells are continuously reorganizing their internal cytoskeleton, constructing the mitotic spindle, and physically pinching their membranes in half. So an embryo might be slightly ahead of the expected schedule or slightly behind it and still be perfectly viable. We have to remember that our clinical timeline is just a human construct superimposed on a biological progression.
Right.
Developmental timing gives the embryologist incredibly useful data points, but cleavage is really just the embryo's first visible proof that the complex machinery of cell division is online and functioning.
So we know the embryo is slicing itself up without growing, and we know we're just catching fleeting glimpses of that process. But Just having the raw material dividing isn't enough if the structural integrity is compromised.
Yeah.
How does the lab know these divisions are actually stable?
Well, when they pulled the dish out to grade this moving target, the assessment is really multi-layered. And the very first layer is just a simple head count.
Just counting the cells.
Yeah. Cell number is the primary indicator of developmental progress at this stage. Like we noted, 6 to 8 cells on day 3 is the benchmark. If the embryologist only sees 3 or 4 cells, it suggests delayed cleavage. The cellular machinery is just lagging behind the expected timeline.
Wait, let me play devil's advocate for a second.
Sure.
If an embryo is slicing itself up using existing energy, and more cells indicate further developmental progression, does the embryo with the highest cell count automatically win?
Oh, I see what you mean.
Like, say the benchmark is 8, but the embryologist finds one with 12 or 14 cells on day 3. Isn't that just a biological overachiever? Is this basically just a math test?
That is a very common assumption among patients, but in reproductive biology, faster is absolutely not always better.
Really?
Yeah. Surprisingly rapid cleavage often requires very careful review. When an embryo divides too quickly, it can be a glaring sign that the cell cycle checkpoints are being bypassed.
The internal security system.
Right, the system that ensures DNA is perfectly replicated before a split. The embryo might be rushing through the division phase and making catastrophic genetic errors along the way. Quality over speed is the rule here. And that leads directly into the second critical grading feature, which is symmetry.
So we're looking at the architectural balance of the blastomeres.
Yeah.
We want to see if the internal fluid was distributed evenly during the division.
Exactly. Embryologists assess whether the newly formed blastomeres are relatively similar in size. When one cell divides into 2, the structural proteins, specifically the actin cytoskeleton, should theoretically distribute the cytoplasm evenly down the middle.
Makes sense.
Symmetrical blastomeres suggest an orderly, well-regulated division. Markedly unequal blastomeres, where you have one massive cell and a tiny adjacent one sitting next to it, suggest the division was chaotic.
Like the structural cables inside the cell pulled unevenly, creating a lopsided split.
Exactly.
That structural balance makes sense. We want the right number of cells, not too few, not too many, and we want an even distribution of the cytoplasm.
Right.
But there's a third major visual factor in the day 3 grading notes, and it sounds incredibly destructive. Fragmentation. What is actually happening biologically when an embryo fragments?
Fragmentation can certainly look dramatic under the microscope. When a blastomere divides, it's not always a perfectly clean surgical break.
Okay.
Sometimes tiny portions of the cellular fluid, the cytoplasm, pinch off and get left behind during the split. We call these fragments.
So what are they exactly?
They are small membrane-bound pieces of cellular debris trapped inside the zona pellucida, but they do not contain any nuclear material. They are not intact cells.
Why does the cell leave that debris behind? Is the membrane just tearing?
Biologically, it relates heavily to localized instability in the cytoskeleton. As the cell membrane pinches down the middle during cytokinesis, if those structural filaments don't contract smoothly and seamlessly, little bubbles of the cell membrane trap some of the cytoplasm and pinch off independently.
Interesting.
Embryologists evaluate what percentage of the embryo's total volume is taken up by this debris and where it is located within the shell.
If an embryologist sees this debris, does that mean the structural integrity of the embryo is permanently compromised?
Not necessarily, and that nuance is vital to grasp. Mild fragmentation is incredibly common in human embryos.
Oh, really?
Yeah, it's not an automatic failure. An embryo with 10 or 15% fragmentation might simply reabsorb some of that fluid later, or push the fragments to the far periphery where they don't interfere with the next round of cell divisions.
That's amazing.
It is. Extensive fragmentation, however, say 30 or 40% of the volume, is a very different story.
Because it's literally bleeding out its own finite resources.
Exactly. It depletes the remaining blastomeres of essential cytoplasm and mitochondria that they desperately need to survive.
Yeah.
It makes the embryo much harder to assess visually, and it often points to a severe underlying stress in the cleavage dynamics.
Right.
But again, it's just one puzzle piece. Some heavily fragmented embryos reorganize and surprise us, and some pristine zero fragmentation embryos completely fail.
So you're analyzing the macroscopic architecture, the total cell count, the symmetry of those blastomeres, and the volume of cellular debris left on the cutting room floor. But all of that is really just looking at the outer physical shell of the cells.
Yeah.
The DNA inside has to be doing something during all this frenetic division. Can the lab see what is happening to the actual genetics?
They can look for proxies of genetic health, and this is where the trained eye of the embryologist becomes incredibly vital.
Because looks can be deceiving.
Exactly. Because an embryo can present a perfectly reassuring cell number, beautiful symmetry, and absolutely zero fragmentation on the outside, but still hide massive internal red flags.
Wow.
The most critical abnormal finding they look for deep inside the blastomeres is called multi-nucleation.
Okay, the normal state of affairs is one single nucleus per cell, one centralized vault for the genetic material.
Right.
So multi-nucleation is when you look into a single blastomere and see 2, 3, or even more distinct nuclear vaults floating around inside it.
Exactly. A normal division dictates that the nucleus divides, the chromosomes segregate perfectly to opposite poles, and then the cell membrane splits right down the middle, leaving one nucleus per new cell.
So multi-nucleation means that highly coordinated dance basically failed.
Yes. The nucleus divided, but the rest of the cell failed to follow suit. Or the chromosomes didn't segregate properly, and the cell was forced to build multiple separate vaults to house the scattered genetic material.
If the cell's a room, multi-nucleation is like having 2 or 3 entirely different competing sets of architectural blueprints unrolled on different tables in the exact same room.
I love that.
The cellular machinery wouldn't know which set of instructions to execute. It creates absolute biological chaos.
That is a brilliant way to conceptualize it. The resulting confusion in cellular signaling is profound. This raises an important question about why this manual microscopic assessment remains so deeply relevant.
Because it tells us about the spindle.
Right. Multinucleation tells us that the complex mechanics of the mitotic spindle, the microscopic cables that literally pull the chromosomes apart, are misfiring. It heavily correlates with chromosomal abnormalities and aneuploidy.
So even if the outer cell membrane looks pristine, multinucleation proves that the internal genetic organization is fundamentally flawed.
Exactly.
It's incredible that you can spot a genetic traffic jam just by observing the nuclear boundaries. But what happens if that internal chaos gets to be too much?
Well,
we know the embryo is running on finite maternal energy, and it's attempting to execute these highly complex divisions. Does it ever just hit a wall and give up?
it does, frequently. And that brings us to the phenomenon of developmental arrest. Some embryos will cleave normally for the first 48 hours and then simply stop dividing entirely.
So you might expect an 8-cell embryo on day 3, but you find it stuck at 2 cells, completely unchanged from the day before.
Exactly.
How does the embryo actually know to stop? Is it just running out of biological gas, or is there an active kill switch being pulled?
It is an active, highly sophisticated internal checkpoint system. Between day 2 and day 3, a massive biological handoff occurs, known as zygotic genome activation.
The handoff from the mother to the embryo itself.
Yes. The embryo transitions from relying entirely on the maternal mRNA provided by the oocyte to actually activating its own unique, newly formed embryonic genome.
Okay.
If that new genome contains severe chromosomal errors, or if the transcription process fails, the embryo's internal quality control sensors detect the critical failure.
So it's doing its own quality control. If the new blueprint is fundamentally unreadable, the biological site manager halts construction rather than building a collapsed house.
Precisely. The proteins required for the next cell division simply aren't synthesized. The cycle halts.
Wow.
And it isn't apoptosis. It's not programmed cell death where the cell actively dismantles itself. It is senescence, a permanent, irreversible suspension of the cell cycle.
Just a hard stop.
Right. Cleavage-stage arrest is one of the very first visible signs of embryo attrition. It tells the lab that the intrinsic biological integrity required to continue simply isn't there.
Let's shift focus to the embryos that do make it through this initial gauntlet. Say we have an embryo that doesn't arrest. It successfully activates its own genome. It has 8 beautiful symmetrical cells on day 3, no multinucleation, minimal fragmentation.
The dream scenario.
Right. Does it just keep slicing itself into tinier and tinier microscopic fragments indefinitely?
Not at all. As day 3 draws to a close, the physical nature of the embryo begins a really dramatic transformation. We start to see something called early compaction.
Visually, what does compaction actually look like through the lens of the microscope?
Well, up until late day 3, the embryologist could easily count the individual blastomeres. They looked like distinct, round spheres.
Almost like a cluster of independent grapes sharing a tight space.
Exactly like that. But as the embryo transitions toward what's known as the morphology stage, it starts expressing specific adhesion proteins, like E-cadherin, on the surface of the cells.
Biological Velcro?
Yes, exactly. These proteins act just like biological Velcro. The cell borders begin to blur as the blastomeres adhere tightly to one another.
So the distinct boundaries just vanish, and the whole thing starts looking more like a solid, smooth, unified mass.
Right. The cells are actively maximizing their physical contact area with one another. From a purely practical standpoint in the lab, this makes exact cell counting incredibly difficult.
And eventually impossible, I imagine.
Totally impossible. But biologically, it is a phenomenal sign. The embryo is no longer just a loose collection of independent cells.
It's connecting.
Right. It's establishing intercellular junctions. It is finally starting to communicate and act as a unified, integrated organism.
So what does this all mean for the actual decisions being made in the clinic? Because we have this incredibly detailed grading system, right? Cell counts, symmetry, fragmentation percentages, nuclear checks, early compaction.
Right.
But you mentioned earlier that day 3 is just a snapshot, so I have to push back here. If an absolutely perfect, top-tier, perfectly symmetrical 8-cell embryo on day 3 can still hit a genetic wall and arrest on day 4, why do we even bother grading them right now?
That's a very fair point.
Aren't we just creating a false sense of security for the patient based on highly incomplete data?
If we connect this to the bigger picture, your pushback is entirely valid, and it really points to the strict limitations of cleavage-stage morphology. A perfect day 3 grade absolutely does not guarantee blastocyst formation.
Okay.
It does not guarantee a chromosomally normal embryo, and it certainly does not guarantee a live birth. But we grade them because in a clinical setting, we have to make critical decisions about resource allocation and patient care today based on the best data available today.
It's a triage system to figure out the immediate next steps.
Exactly. If a patient has a cohort of 8 embryos, the day 3 morphology helps the lab stratify that group. It tells the embryologist which embryos are the current biological frontrunners.
Okay.
If the cohort looks generally weak, highly fragmented, or delayed, a clinician might decide a day 3 transfer into the natural uterine environment is the best chance for success, rather than risking them in the artificial culture.
That makes total sense.
But if the cohort is robust, showing strong cell counts and early compaction, it gives the lab the confidence to utilize extended culture, keeping them in the incubator until day 5 or 6 to see which ones actually possess the genetic competence to form a complex blastocyst.
So it is absolutely not a crystal ball. It's an incredibly detailed, real-time progress report.
Yes.
The perfect day 3 embryo might still fail the final genetic exam on day 5, and an average-looking, slightly unsymmetrical day 3 embryo might reorganize itself beautifully during compaction and become a stunning blastocyst.
That is the perfect way to summarize it. A day 3 embryo is a developing possibility, not a definitive prediction. The cleavage stage is simply the embryo proving it has the mechanical capability to divide and activate its genome.
We have covered a tremendous amount of ground today. We started with the sheer physical mechanics of the cleavage stage. That frantic microscopic slicing of a strictly finite volume encased in the rigid zone of pellucida. We moved past the simple mathematical cell count to understand the vital structural importance of symmetry and how the presence of fragmentation points to the sometimes messy reality of biological division.
We also looked beyond the cell membrane, unpacking how multi-nucleation reveals chromosomal chaos hiding in plain sight, and how developmental arrest acts as the embryo's uncompromising quality control system during the critical handoff from maternal to embryonic genetics.
And finally, we saw those distinct cellular boundaries literally begin to blur with early compaction, signaling the end of independent division and the dawn of a unified structure. I want to thank you for joining us on this deep dive.
We appreciate you being here.
The microscopic world is incredibly complex, but understanding the biological why behind these lab reports takes a little bit of the mystery out of the waiting game.
It certainly does. But before we sign off, I want to leave you with one final, deeply provocative thought to mull over.
Oh, I like these.
We established that the cleavage stage is an exercise in identical division. 1 cell becomes 2, then 4, then 8 functionally identical blastomeres. Right. But as they compact and bind together, a profound biological mystery arises. If every single cell in that embryo is identical, possessing the exact same DNA and sharing the exact same cytoplasm, how does this uniform cluster suddenly know how to break symmetry?
Wow, yeah.
How do perfectly identical cells decide over the next 48 hours which of them will become the placenta to nourish the pregnancy and which of them will become the actual human fetus?
That is a million-dollar biological question, and that is exactly what we are going to explore next time.
We are.
In our next deep dive, Episode 10, Reaching Blastocyst, we are going to follow the embryo right past the blurring lines of day 3, straight into days 5, 6, and 7.
It's a fantastic journey.
We will look at expansion, the inner cell mass, the trophectoderm, and how this tiny cluster of identical cells finally begins to organize its destiny.
Until then, remember, even the most complex, beautiful systems in nature start with a single, simple division.
Thanks for listening. We will see you on the next deep dive.